I want to introduce our next speaker from Recogni, Mr. R K Anand. Come on out, sir. Give him a warm welcome.
Good morning, everybody. I hope everybody's enjoying the day today. You're going to try and wonder why the topic today from us is about AI is cool, but show me the money. And when we're in an infrastructure conversation, right? And so I think eventually, whatever we build in infrastructure has to end up in the economics of serving AI. And what matters eventually is that today the currency of AI, when everybody talks about the currency of AI, it's in tokens. And there's a shift happening in how AI is consumed, how these models perform, and how eventually money gets made. Because the economics of AI eventually means that customers who eventually use AI will pay for it. The providers of the infrastructure and the providers of the models will have to make money in that exercise. So today it's still unclear who's making money. You might hear about revenues, but you may never hear about the profitability of AI yet. So let's look at it, right? The tokens era is quite confusing. For a lot of us who use models, I'm sure a lot of you use AI models every so often. You look at three models here, right? Varying input cost for input tokens, varying costs when it comes to cached inputs, how much it, whether it, in the case of DeepSeek, it's, $0.55 for 1 million tokens, versus at OpenAI, actually from the input tokens to cache tokens, they probably have a much better caching hierarchy that allows them to actually deliver tokens less expensively when it's cached. And then output tokens have variable costs. But if you look at the plethora of models available to all of us, we don't even know which model to pick for what task. There's variability in the kind of quality of results, the experience, the pricing. How much does it cost? If you look at it in the case of DeepSeek, it's cheaper if you want to use it at a different time, maybe in the night. In the case of Anthropic, it's cheaper if you batch it and you don't do real-time work with it. So all of these will eventually play to the economics of the infrastructure that we all will build for the use of AI broadly. So let's look at the world in terms of how it is transformed in the last year. Last year, in the beginning of 2024, it was only LLMs. And large language models had this unique property where if you gave it an input, the amount of time taken in compute was fixed. It wasn't variable, and then you get an output token. So you could measure input tokens, output tokens, and because the predictability of the model through the infrastructure was well-defined and not variable, you could know how much to charge for it. Well, late in 2024, we started seeing the chain of thought models or reasoning models. And these reasoning models eventually start with a set of input tokens, but then they loop within the system for a while before you get an output. So now you have a variable piece of time where you're consuming tokens, you're consuming energy in the infrastructure, but you will eventually deliver answers. So now you go from a measurable mechanism to something that's variable. And then on top of that, now in 2025 and beyond, we are talking about agents. When you shift to the agentic approach, you're going to use either language models or chain of thought models in a chained approach. And now you add another layer of variability on top of it. So complexity and variability now start playing a role in assessing the economics of AI and how much infrastructure, how much inference infrastructure is being used and consumed to do this work. So you have to think about this more comprehensively as infrastructure providers, because the economics of AI will eventually determine the success of AI and the ubiquitous use of AI. So as we all build infrastructure, we have to think about how we can deliver it less expensively and more certainly at a lower cost for eventually the providers or the users of the infrastructure, the developers of models who will run this over on this infrastructure, and then the end users of applications. So let's do an experiment, right? And run a prompt, the same prompt 100 times over. And you take a simple model, a large language model that, like I described in the previous slide, has a fixed amount, that deterministic period of answers. And the other is models that have complex reasoning. So they take a variable amount of time and you get variable set of results. And let's think about the consistency of the results and compare the output token information as these systems perform their work. So the two models, the one on top is a reasoning model. And you look at it, when you give it 100 such prompts, the same prompts, you get a variable set of compute time and a variable set of tokens being consumed by the machine before it gives you the answers. And then the bottom is a standard language model, which has a more fixed characteristic, and it gives you a set of results that have less variability in terms of the amount of compute time being taken. So in the case of the reasoning model, you have 54% of indeterministic kind of characteristics. And so it costs more, and it's unpredictable in how much more it costs because it changes depending on when the tokens are executed and what the results look like. In the case of a large language model, it's more predictable and it's more deterministic. And so you can actually charge more in a more reasonable manner. So this variability is quite a challenge. So we define it at Recogni as the Heisenberg Uncertainty of AI inferencing. And you say, well, if the costs become more predictable, the quality declines. Why does that matter? Because if you take a large language model, you could get responses that are quick, predictable, less expensive, but maybe not the right set of answers. These models sometimes tend to hallucinate. And then if you look at the large language models, you can't use them for formal business processes. If you want to do financial analysis, if you want to do maybe finite element analysis or analysis of other complex workloads, you want models to give you what you think are trust answers that you can depend on. If you now say, let me just make it more predictable, you will now use a large language model. But can you use a large language model to give you a mathematical answer accurately every time? Pretty unlikely. So the way we think about it is that you actually, as infrastructure companies, we have to build infrastructure that can process as many tokens as possible at the highest quality. That means that you need to build systems that can actually deal with these larger models, more complex reasoning models that can take a lot more time, a lot more compute, and can re-ingest responses or tokens before giving you the final answer. This will result in 10 to 100x more compute. So imagine a large language model, and from there going to a reasoning model where you need to consume 100x more compute. Imagine the cost implications and eventually the revenue and profitability implications of people who will provide that. Well, how do we solve this? So at Recogni, we spend a lot of time thinking about this from first principles. We are an infrastructure inference company. So we think about AI. If you think about AI fundamentally, token in to token out, even in a large language model, just to get one token out takes trillions of operations. And all of AI is basically matrix operations, matrix multiplications followed by matrix additions. So we started at Recogni fundamentally changing the math of how we do AI math compared to the rest of the industry. So we do the AI math multiplications using logarithmic math. We get the same dynamic range of floating point math, but multiplication becomes adders, and addition means you can pack more addition in real estate and silicon. When you pack that, you consume less power. There's significantly second and third order benefits when you do this. So first, start with the math. That means that you have to have compute density that's competitive with the rest of the industry, but you consume a lot less power. So then there are operational benefits that accrue to customers. Well, now you have a compute engine that does math more efficiently than the rest of the world. Well, you need memory that's in proximity to these compute engines. So we spend a lot of time, because we free up real estate and silicon, and we're not doing traditional floating point math, we have the capacity to put more memory, SRAM, closer to our compute engines. That results in bandwidth advantages and the ability to keep those engines busy and occupied. You still need a high bandwidth memory, high capacity memory in near proximity. So you cannot avoid putting HBMs in silicon for AI. But the nature of AI compute is to have significantly higher, almost 10x more bandwidth of local memory close to your compute. So that's the second part of the story. Now, the third part of the story is that the models have gotten so large, so large that they cannot fit on a single device. So today, you can actually take a Llama 70 and put it on an H100 or H200. But the minute you go to a Llama 4 or 5B, it's a 405 billion parameters, and you need to straddle it or shard it or do what's called tensor parallelism over 8 GPUs, in the case of NVIDIA H100s. That is the challenge that's across the whole industry. It's not unique to us, it's not unique to AMD, it's not unique to NVIDIA. So when you think about it, you actually have to have a really high-speed interconnect that connects these chips together. That is a fundamental problem in AI inference. You have to have these chips connected together because the model does not fit on a single device, and you need to be able to shard the model across many devices and then get incredibly high performance out of it. So again, 3 parts of the story. Denser compute consumes lower power, gives you real estate to put high amount of memory next to your compute, and then you need to connect these chips together. All of these things are essential for eventually delivering the value that people care about. Finally, you need software that allows you customers to take trained models and then compile and quantize them onto your devices. And that needs to be a flawless, seamless experience so that they can actually deploy models rapidly as these new models arrive, and do it really well for multi-trillion parameter models and gain the highest utilization of the hardware. So what does the world need? The world needs as many tokens as possible. Whether they are large language models, diffusion models, chain of thought models, in all cases, we need the ability of the hardware to deliver this at the most economic and most advantageous and lowest power capability. So today, the workaround is, let us make more compute more expensive, and then let's drop precision. That means that this recommendation is, well, FP8, I cannot deliver enough compute, so why don't you go to FP4? That is the wrong answer in our opinion, because now you are now reducing the quality and the reliability of the output of the models. So it's essential that you deliver precision at a high precision first, but also make sure the compute is less expensive and consumes less power operationally for data center operators and hyperscalers. So our recommendation is that hardware systems need to be evaluated that promise the future with metrics that tell us results that are truthful, that are accurate, essentially meaning that the ability of people to run more complex models, more chain of thought models, and string them together because we need results that we can depend on for AI. You cannot have AI become a tutor to a student and teach them mathematics or physics or biology incorrectly. It has to give you them right answers so they get educated the right way, as an example. So we really need an AI inference reality check. And one has to think through this really carefully because we are at an inflection point where you cannot brute force this. You cannot just throw more hardware, more power consumption, more racks at the problem because the economics of AI will start to fall apart. So it's essential to think through this very carefully. So if there's one takeaway for all of us in the industry that's building infrastructure, and it's an inference reality, and you should check the following metrics, right? Does your hardware, your unit, whatever the unit may be, deliver the most amount of total tokens per second? Like I said, tokens is the currency of AI. Second, does it on a CapEx basis deliver the most tokens per unit dollar of CapEx purchase that you buy from vendors? So if you're an infrastructure provider that's going to sell to hyperscalers, tier 2, 3 cloud providers, and others, you need to be able to deliver the most amount of tokens for a given model than anybody else in the world. And then the third, if you heard the prior speakers in terms of energy availability in the US and most other parts of the world, you need to be able to deliver it at the lowest energy consumption in the world. So it's a combination of all of these that's critical for us. So if you're interested, I'll keep this slide up a little bit longer. We have a webinar on what we are building as Recogni, me, my co-founder Gilles Bacchus, and Ian Cuttress will have a talk about this on the 15th, 8 a.m. to 9 a.m. Pacific time. We're more than happy for you to join in. We do not have any products today. We are not announcing, we're not shipping, we're not talking about any products. We're talking about the fundamentals of AI and the economics of AI, and that has to be sustainable for all of us so that AI gets more broadly used. Thank you very much.